Please see me for the current year review schedule. This is just for 2017. The exam information, a little bit about the AP exam. The multiple choice section has two parts, A and B. Part A is the first given. There's no calculator. It's 30 questions and 60 minutes, so 2 minutes per question. Part B allows you to use a graphing calculator. It's 15 questions, 45 minutes. So this is where you want to do your f-ints and your n-derivs and stuff like that. Just a note on the multiple choice questions. College Board has choices A through D on multiple choice. My tests have A through E, so kind of keep that in mind. You have one fewer choice on the actual AP exam. So it's a 1 in 4 chance instead of a 1 in 5 chance, which is a good thing. And also keep in mind that you never want to leave a multiple choice blank. You always want to guess if you don't know exactly what the answer is. The free response question also has two parts. The first 2 questions you get a graphing calculator and it's 30 minutes. The last 4 questions you don't get a graphing calculator and that's 60 minutes. And during this last 60-minute time frame, you can also go back and work on the 2 calculator questions if you want to. You just have to do so without a calculator. Just a quick rundown of really common questions that they ask on the free response. No particular order, but one of the questions will definitely be a particle motion. It'll be some sort of position, velocity, and acceleration. It'll be some sort of relationships where, you have the position, you take the derivative, then you get the velocity, you take the derivative again, you get the acceleration. So multiple derivatives so that you can do derivative tests. You can find zeros, you can do concavity, you can do points of inflection, you can do mins and maxes, all of that stuff. Mins and maxes, hills and valleys. So speed, total distance, speed is the absolute value of velocity, total distance is the absolute value of position. Make all regions positive as you integrate. Average velocity is algebra. It's an algebraic slope of the position time curve. Another question is going to be an accumulation question. So this is accumulation means integration. So a lot of times it's a rate question. So like falling snow, how much accumulates over time. So integrating a definite integral. Average rate of snowfall. So taking the integral and dividing it by the time the time passed to get the average rate. What time is the snow falling the hardest? So the maximum rate. So looking at that rate and finding a min or a max, so finding where its derivative is equal to 0. And a lot of times they'll add a section where as something is accumulating, something is being removed. So part D, it's like if as it's snowing, I'm shoveling, or as it's snowing, the snow is melting. So it's basically taking that rate and subtracting something from it that's causing that snow to go away, and then integrating that. So the third question is kind of a potpourri, not because it smells good, but because it's the catch-all where they do any topic just so that after they look at the test and they realize what they're a little low on, they kind of insert a bunch of stuff in that one question. So it could be a related rates, like a ladder sliding down a building. It could be a differential equation, separable, so that you have to integrate it, an initial condition sort of thing. It could be implicit differentiation, okay, which kind of goes back to related rates, where you have to do the, differentiating the y and doing the y prime sort of thing. Definitely one of the problems is going to be a differential equation problem, just like on the unit exam before this last unit. Graphing a slope field, separating and solving a differential equation, maybe graphing the particular solution on the slope field, maybe writing an equation for a tangent line. to that differential equation. So using the differential equation to get the slope, and then using that point to get the slope point form, that sort of thing. One of the questions will be an area volume problem, just like the last unit. Finding area between curves, finding a volume of revolution, finding a volume of known cross sections if you put squares on there, or maybe semicircles. Very rarely do they ask you about triangles. Usually squares, rectangles, and semicircles. And then the last type of problem is a tabular problem. So this is where they're going to give you a table, and if the table only has 3 or 4 points in it, they're probably going to ask you for a left or a right Riemann sum, or maybe a trapezoidal sum. That's averaging left and right. Sometimes with uneven widths, so you have to do each area separately. If they give you a lot of points, like 10 points, then they're probably going to ask you for a midpoint, where you can group 3 points together and pick the middle one to calculate the height of to find the height of your triangle, or the height of your rectangle. And then this is where they explain the units. So when we're talking about Riemann sums, we're talking about integration or accumulation. So we're multiplying the units that we see. Or going back to the table, they might ask you to do an average value, which would be, taking that integration and dividing it by the interval width, or an average rate, which is different, right? The average rate is a slope, so this is just algebra. So they would have you take 2 points and do a slope between those 2 points, and then talk about the units. So if we're talking about a rate, then we're talking about dividing the units. So those are kind of the 6 types of problems that are really, really typical on the AP exam. So you have kind of a summary of that information, so you can kind of refer back to it and make sure you can hit each one of those skills as we enter the differentiation and integration portion of our review. But for now, for this video, we're really reviewing limits, and then we're going to talk about L'Hopital's, which is a way to evaluate limits, which is much more efficient than some of the other strategies we used in the past. So when we're talking about limits, we've got a Mean Girl video here that kind of has to do with limits, so we're going to go ahead and show that.
Contestants, find the limit of this equation.
Calling somebody else fat won't make you any skinnier. Calling someone stupid doesn't make you any smarter. And ruining Regina George's life definitely didn't make me any happier. All you can do in life is try to solve the problem in front of you.
The limit is -1.
Oh, crap. I lost.
That answer is incorrect. Now, we are in a sudden death. If Miss Heron can answer this problem correctly, we have a winner.
Limits. Why couldn't I remember anything about limits? Limits. That was the week Aaron got his haircut. Oh, God, he looks so cute. Okay, focus, Katie. What was on the board behind Aaron's head? If the limit never approaches anything, the limit does not exist. The limit does not exist!
Our new state champions, the North Shore Mathletes.
From the AP test, you're going to experience that level of elation and that level of dominance as you ace the AP test. Okay, so as we go back to our AP test, as we go take that AP test, that's a level of confidence that you should go in with for sure.
So in the movie Mean Girls, Lindsay Lohan is tasked with finding this limit.
Forgot to stop the video.
To know on the AP exam, but it is a useful
technique. Let's try that again. There we go. All right, so as we're talking about limits, just like Lindsay said, if it never approaches a value, then the limit does not exist. Single value. So a limit is an approach value. So we had this earlier this year. We're just going to go through this again. We're going to focus on what happens as we approach 1, the x value of 1. So remember that we can approach from the left side, so you've got left-hand limits, or we could approach the value from the right-hand side, which is called the right-hand limit. So we're going to look at this location here. And so as we approach from the left side, or the littler side, that means we're coming along that part of the piecewise function. And so what y value are we going to? We're approaching the y value of 0. So the limit, the left-hand limit, at 1, approaching from the left, or that's what the little negative sign means, is 0. Okay, that little negative sign means approaching from smaller values. Okay, let's look at approaching the same location from the right-hand side. So we're taking the limit as we approach 1 from the right, or the bigger values. That's what the plus means. And as we're approaching from the right, we're approaching a y value of 1. So since our left-hand limit and our right-hand limit are different, then we say that the limit does not exist at 1. Remember, that limit is that overall comparison of these two values. In other words, we're not approaching the same location on the coordinate plane from both sides, so our limit can't exist. Just a quick mention about function value and the difference between limits and function value. Function value is where that dot is filled in. So when we look at this location, our dot is filled in up here, 3. So the function value is 3. Notice we can, to talk about left and right hand limits, we can have a left and a right hand limit even though we have an open dot there. And we'll talk more about that as we get to this point as well. So let's kind of fill in this table here. Next point we're going to talk about is when x equals 2, when x approaches 2. So we're going to talk about this location. So when x approaches 2, the left-hand limit is approaching 1, and the right-hand limit, as we come from the right side, is also approaching 1. So that tells us, since these values are the same, that we're approaching the same value. So the overall limit is 1. Okay, we'll talk about the function value, but notice a limit exists here even though there's an open circle at that location. Let's talk about 3. We'll talk about function values and continuity a little bit later. So now we're going to talk about this location, x equal 3, x approaching 3. So if we approach it from the left, we're approaching a y value of 2. If we approach this from the right, again we're approaching a y value of 2. These two values are the same, so the limit exists, and it's 2. Now let's look at our endpoints here, because our endpoints, since our piecewise function begins and ends, begins at 0 and ends at 4, we have one-sided limits at our endpoints. So as we look at approaching 0 here, we can only approach it from the right. So a left-hand limit doesn't exist, or is not really applicable, because we can't approach it from this side. Our function doesn't begin until 0. But we do have a right-hand limit. We can approach it from the right side, and as we approach it from the right side, we're approaching a y value of 1. And since it's an endpoint, we only need one of these. So since we have a right-hand limit that exists, we have an overall limit of 1. And then let's look at the other endpoint, 4. And the left-hand limit at 4, we can approach it from the left. So we're approaching a y value of 1 again. And from the right-hand side over here, since the piecewise function ends at 4, we can't approach it from larger values. So again, this is not applicable. You can also say it doesn't exist. That's fine. But again, since it's an endpoint, and we have a defined limit from within the domain, we know that we have an overall limit, and that limit is 1. So limits exist because, so this is a box on your notes next to the graph. And the limit exists because our left-hand limit, that's the minus sign, right, approaching from the little values, and our right-hand limit are equal. So when we look back at the table here, the limit exists here because our left and our right are the same value. Also here, left and our right and our same value. And then it exists at the endpoints because we have defined limits at our endpoints. So you can either say that in a mathy way, the left limit and the right limit are equal, or you can just use words, left and right hand limits match. So either way, get that down in the box, whether you want to use the mathematical representation or just jot down some words. We're going to go on now and start talking about the function value and continuity. So function values, we're looking for those closed dots. We know at x equals 1, the function value was 3. We already filled that in a little earlier. Okay, so we know that's 3. Let's take a look at when x equals 0. Where is the filled in dot? And the filled in dot is right here. So the function value is 1 there. Okay, now let's look at x equals 2. Where's the filled in dot? It's right here. That's a y value of 2. So the function value is 2 there. Let's look at 3. The filled in dot is right here. So function value again is 2. And then let's look at 4. And when we look at 4, we see that we have no dot filled in at all. So we do not have a function value then. It's just an open circle. So that function value doesn't exist at 4. If you remember continuity, continuity is the existence of, well, continuity is looking for the existence of discontinuities. Remember, discontinuities are removables, which are just holes that aren't filled in. They're jump discontinuities, where our function takes a jump in value up or down. They're asymptotes. They're oscillations. Those sort of things ruin our continuity. So if we look from left to right here, we're going to look for gaps and jumps and asymptotes. We don't have any asymptotes and we don't have any oscillations. So we're really looking for holes in our data or things that cause us to jump. So if we look at x equals 0, we have no holes and we have no jumps. And if we notice our limit and our function value are the same, that's really the definition of continuity. So we have continuity here. Since these values are the same, we have a filled in hole. Okay, as we go out then to the function, as we go to x approaches 1, we notice that we have a jump here. So since our limit and our function value are not the same, we would have to literally lift our pencil in order to get transition from here up to here to fill this in, and then down to here to continue on the piecewise function. So we're jumping all around at x equals 1, so we have no continuity at that point. And then we can go ahead and transition from 1 to 2. It's all nice and continuous here. And then when we get to 2, again, we look at the fact that our limit is 1 and our function value is 2. So as we approach 2, we have to draw an open dot here, and we have to jump up here and fill in a dot up here, and then go back to the same location down here. So we call this a hole or a removable discontinuity. So again, since we had to lift our pencil to get up to here and then come back down, we have no continuity at that point. And then as we transition from 2 to 3, it's nice and smooth. So we're continuous here. And then when we get to 3, we notice that our limit and our function value are the same. So in other words, as we approach 3, we can stay right here, fill in the circle, and go on our way. So we don't have to lift our pencil. So we have continuity at 3. And then as we transition to 4, this is all nice and continuous as we go from 3 to 4. But as we approach 4 again, our limit and our function value are not the same. So we have to come here and we have to lift our pencil. We can't draw anything at 4. So we do not have continuity at 4. So in terms of continuity, and you have a box here, again, next to this graph to put in your thoughts about continuity. The mathematical definition is the fact that the limit equals the function value. So looking back at the table here, limit and function value are the same. Yes, we have continuity. Limit and function value are different. There must be a discontinuity there. Different again, there's a discontinuity. So this was a jump, this was a hole or removable. Limit and function value the same, so we have continuity there. Limit and function value different, we have discontinuity. Again, we have a hole or removable. So you can use the mathematical definition, or you can just jot down a quick sentence. The limit and the function value need to match. That's what needs to happen for continuity. So that's it kind of goes over the big ideas behind limits, function values, and continuity. So now we're going to try this and we're going to kind of move away from graphical representations into algebraic representations and how to determine that algebraically. So let's take a look at this. We've got a piecewise function and we want continuity when x is equal to 2. So we know if we want continuity, that means our function values have to match. So in order to figure out what value for k would cause these to be the same, we set them equal to each other. So we're going to set x squared minus 3x plus 9 equal to kx plus 1. And we want to evaluate this when x is equal to 2. So we know we can stick the 2 in for all these x values. So we're going to go ahead and do that. And then we notice that when we stick 2 in for all those x values, we can solve for k. So this left-hand side is going to be 4 minus 6 plus 9. and the right-hand side is just 2k plus 1, and then doing this is 7. So what value of k makes this right-hand side equal to 7, and that's a k value of 3. So the answer here is C. K value of 3 will force continuity in this piecewise function. So when k is equal to 3, we stick it in here, the function value is equal to 7. And when k is equal to, well, we don't have a k here, but when x is equal to 2, this function value is 7. Those function values match. Just a comment before we jump into algebraic evaluation of limits. And it's just a comment on fractions. All these 4 fractions we are able to determine their values. So 1 over a really big number, like 10's not so big, but 100's getting bigger. 100,000 would even be bigger. Of course, the biggest number we know is infinity. So 1 over a really, really big number is 0. 1 over a really small number, so 1's not so small, but 1/100th is getting there. Or 1/100,000th. Or basically our lowest magnitude number that we know is 0. 1 over a really small number is infinity. Or we could say does not exist. That would be another option for this answer. Or undefined would be another option. We use those 3 things interchangeably. 0 over any number, like 7, or negative 216, or even a really big number, like 123,456, or even a bigger yet number in magnitude. But we have a 0 on top, so we know that that's 0. And then if we take any number over 0, this is our big undefined, right? So this is, again, infinity or undefined or does not exist. This is our vertical asymptote. We'll come back to that comment a little later on. So now that we kind of know that we can really assign those values, let's start looking at evaluating limits. This is kind of taking a step backwards. So if we have, like our piecewise graphs, if we have accessibility to a graphing calculator, go ahead and graph it. So sine of x over x. If you have a graphing calculator, remember sine of x over x looks like this. Okay, as x gets bigger and bigger, this denominator causes this oscillation to kind of go away because the denominator is getting bigger and bigger. So we know that sine of x is the biggest value is 1, so it's depleting that amplitude. So as we approach 0, we can see that from the left and the right, we approach a value of 1. So the limit here then is just that function value 1, and we can see that graphically, or we could look in the table at x equals 0 and see on either side of it what value is really, what value, just on either side, what value the function is, as we zoom in on our table as well. Okay, so now let's talk more about numeric or algebraic solutions when you don't have a graphing calculator. So when we talk about this limit, if we can just plug in the 3 and get a finite answer, or one of those fractions from before, then we can evaluate it. So plugging in 3 here gives us 7 over 8, so the limit must be 7/8. Plugging in infinity here, as we approach infinity, remember this is called the end behavior, because we're looking at the end of the function, way out at infinity. So remember, that gives us leeway. That allows us to say things like the 16 and the 1 are small, so they doesn't matter. And then the powers are the same, so the magnitude, top and bottom, are the same, so those can cancel. So we're left with 5/3 after we do all that estimating. So we get that leeway as we approach the ends of our functions. That's that end behavior. And we also know that since we're way out at the ends of the function, if they're approaching some y value, that means that function is becoming horizontal, getting close to a horizontal asymptote. So y of equals 5/3 is a horizontal asymptote. Let's take a look at this function again. Remember what it looks like. as we approach the ends. In this case, we're approaching the left end, negative infinity. So we know that oscillates and gets closer and closer to 0. But if we think about it numerically, we know sine, its biggest value is 1, so that's the biggest the numerator can be. And we can plug in infinity at the bottom. This is 1 over a really large magnitude number. We know that as 0 from our fractions a little earlier. And again, that's a horizontal asymptote too, because we're approaching the ends of the function. That's our end behavior. So we have another horizontal asymptote at y equals 0. So limit questions can look of one of two forms. A limit question can just be a straight expression that you evaluate, or a limit question can be kind of disguised by asking you to find horizontal asymptotes. Limits can also be disguised by asking you to find vertical asymptotes. That's when the denominator is equal to 0. Okay, like this one. So if we plug in 2, we get 5 over 0. We know we can evaluate that as a number over 0, that's infinity. So we say that the limit doesn't exist. Okay, so at 2, these values just get really, really large. Okay, and so that's a vertical asymptote. When we set the denominator equal to 0, we find vertical asymptotes. So again, limits, you can have algebraic expressions to figure out, or we can disguise the question by asking you to find horizontal and vertical asymptotes. Those are limit problems. If we ask you to find a horizontal asymptote, we're asking you to take the limit as x approaches infinity and negative infinity. If we're asking you to find a vertical asymptote, we're asking you to look at the denominator and set it equal to 0. So we have a vertical asymptote at x equals 2. So how about this one? Can we plug in infinity and square it? And the answer is yes, we can. We just still get infinity. So this limit doesn't exist. It's not an asymptote because we have no denominator. This value, this is a parabola. We know that when we get really large values of x, we just get really large values of y. So this thing just keeps going up and up and up and up. So that's an infinite limit, or it does not exist, or it's undefined. Again, any of those answers would be just fine. The problem with plugging it in is that when you get 0 over 0 or infinity over infinity, you can't evaluate that numerically. So that just means we have to do another strategy. So if you remember that one of our strategies was to algebraically simplify the expression to see if that helps us eliminate this scenario. So let's take a look at this. So if we plug in 7, the top is 0 and the bottom is 0. So that's this scenario. So we can't evaluate that. If one of these were a number, we could evaluate it, but neither is, they're both 0, a non-zero number. These are both 0, so we have more simplification to do. So we notice the top is factorable, so we go ahead and factor the top, and then we cancel what we can, and that gets rid of the denominator, which gets rid of the problem. So we're being asked to find the limit of x plus 7 as x approaches 7. So now we can go ahead and plug in the 7 and get a finite value, 14. So the limit must be 14. So if we remember this, when we graph this is a line with a hole at x equals 7. If you remember this line. When you can't factor, we have something that's called L'Hopital's. So this is the new content here. L'Hopital's involves calculus simplification instead of algebraic simplification. So L'Hopital's kind of goes like this. For instance, this is not something that's factorable. We can't cancel the x's. This x is inside the trig function. So if we can't use algebraic techniques, we can use a calculus technique here. So we know what sine of x over x looks like. I've had the graph up twice now, right? It looks like this. We know that as it approaches 0, the limit is 1. So we know the answer here. And we're just going to use this process to confirm that the answer hasn't changed. So we know that the answer is 1, right? As we approach 0, we know the answer is 1. So let's take a look at this from a L'Hopital's perspective. Okay, we plug in the 0, the approach to value. We see we get 0 over 0, which is one of the forms that says, hey, I need to use some simplification here. We can't factor, so we can't use that simplification strategy. So we're going to use L'Hopital's. L'Hopital's basically says this. We have what we call an indeterminate form. That's the 0 over 0 or infinity over infinity. And So as we approach 0, we have to use a different strategy. So we're going to take the derivative. We're going to differentiate the numerator and the denominator. Okay. Just a quick note, this is not using the quotient rule. This is taking the top and taking its derivative, and then taking the bottom and taking its derivative, and making another fraction. So we're going to go ahead and do that. So what's the derivative of sine? That's cosine. What's the derivative of x? That's 1. So we have this, which is just cosine of x, right? Cosine of x over 1 is just cosine of x. So if we superimpose cosine of x over our sine of x divided by x, we see that as we approach 0, the two expressions approach the same value. And that's what L'Hopital says. L'Hopital says that if we have an indeterminate form, we can differentiate, and the derivative will approach the same value as the original function. So if this is able to be evaluated, then this answer we know is going to match the original answer. So now we can plug in 0, because we know cosine of 0 is 1, and 1 over 1 is 1. That's not indeterminate. We can determine that. So we can see that the limit of this is 1, so we know that the limit of this must be 1 as well. So just to kind of put that into words, we start with a rational expression. We start with a fraction. There it is. There's our fraction. If this ends up being 0 over 0, as we put in this value, or infinity over infinity, okay, then we have to use simplification. Okay, so let's pretend the substitute in C. Let's pretend we get numbers. Well, then that's the limit. Let's look at the other scenario. Let's say, yeah, it's indeterminate. It's either 0 over 0 or infinity over infinity. Then we need to simplify. So if it's not factorable, and we can't use algebra, then we go ahead and differentiate the top and the bottom. And we plug in C again. So here's the derivative of the top, and here's the derivative of the bottom. We plug it in. We plug C in again. And if it's still 0 over 0 or infinity over infinity, then we go back and differentiate it again. And we keep doing that until we no longer have this form. And if we no longer have this form, that means we're up here and we can find a value. Okay, but every ratio of the derivative will be the same as this as long as this is happening. So L'Hopital's is, it was developed by actually a person by the name of John Bernoulli. That might sound familiar to some of you physics folks. And then L'Hopital's kind of formally proved that this in fact does hold true for indeterminate forms. And there's Bernoulli. So if we look at some other examples, for instance, let's consider this. Now we're approaching infinity, so we can do our end behavior strategy, which is already written in your notes, right? We know that we get infinity over infinity here, so it's indeterminate. So we can do our end behavior technique here. We can say this can be ignored because it's tiny, which leaves us with that. And then if we have that, this can be canceled, which leaves us with that. And so the limit is 3/2. Okay, so that's our old technique. Let's try our new technique to verify that we get the same answer. So using L'Hopital's rule, we start with the original expression. We take its derivative. So the derivative of the top is 6x. The derivative of the bottom is 4x. We notice that this is infinity over infinity. So we take a derivative, we get 6x over 4x. We plug in infinity again. We notice we still get infinity over infinity, even though we've already taken the derivative once. So we do it again. So the derivative of 6x is 6. The derivative of 4x is 4. So now we have this form. And when we try to plug in infinity, we can't. So we have a finite ratio, 6/4. And if we notice 6/4 reduces to 3/2. So we can see that the limit is 3/2 using 2 rounds of L'Hopital's. So This one, we can still go back to our end behavior approach, or we can use L'Hopital's, totally your choice. So let's take a look at this one. This one we could simplify. So we could look at this. As we approach 2, we get 0 over 0. That's that other form. That other indeterminate form. And again, you have this all written out in your notes. I didn't want you to have to write it down. So if we go back to the old approach, when we talk about having these indeterminate forms, we can go back to our factoring method. So we can go ahead and factor this and cancel and be left with the limit as x approaches 2 of x plus 2. And if we plug in 2 now, we no longer get an indeterminate form, we get 4. So we know the limit's 4. So again, this is a line. When we graph this ratio, we actually get this line. So intercept 2, slope of 1. And then as we approach 2, we have that open hole. But on either side of 2, that line passes right close to 4. So let's try L'Hopital's now. This is where you're taking notes. So using L'Hopital's, we're going to take the derivative of this, which is 2x. That's the top. And then we're going to take the derivative of this, which is 1. And then we're going to plug in 2, and we notice that when we plug in 2, we no longer get our indeterminate form. We get 4 over 1, which is 4. So we get the same limit using L'Hopital's. So I just want to reiterate that using L'Hopital's is for these special situations when you have 0 over 0 or infinity over infinity. Okay? And it's particularly useful when we can't simplify. So we can always, factor and simplify, but it's particularly useful when we can't simplify. So if we look at the top and the bottom of this particular example, and this is just not in your notes, but just looking at this graphically, x squared minus 4 is this parabola, and x minus 2 is this line. And as we approach 2, we can see that both those values approach 0. So that gives us the ratio of 0 over 0, right? And if we keep zooming in, we can see, yeah, that's definitely 0 over 0, right? So if we take this ratio of f of x over g of x, somewhere close to 2, if we look at that ratio, we see f of x is pretty tall, g of x is pretty small, and we can see that it's the same as taking the derivative of the top and the derivative of the bottom, which ends up being 4. So that ends up being the L'Hopital's rule. Is if we have this indeterminate form, then we can take the derivative of the top and the bottom. So we're going to gloss over this because it's really not that important. Let's go to the example here. So this would be one you couldn't graph because of the variables in here. And this is one we can't factor, so we're going to have to use L'Hopital. So as we plug in 0, we have sine of 0 over sine of 0, which is 0 over 0. So we need to use L'Hopital's. So we have to take a derivative of the top. Remember, this is a chain rule here. So the derivative of sine of ax is a cosine ax, right? It's the derivative of sine, which is cosine, and then the derivative of the inside, which is a. And then likewise, the derivative of the sine of bx is b cosine bx. Now substituting in 0 for the x values here, cosine of 0 is 1, so we get the ratio of a over b. So this limit is a over b. So if a were 5 and b were 2, this limit would be 5 halves. Let's take a look at this. Again, we can't factor this, but when we plug in 0, we get 1 minus 1, which is 0, and 0 plus 0, which is 0. So we need to do something to simplify this, and we can't factor it, so we're going to go ahead and do L'Hopital's. So the derivative of the top is the derivative of 1 minus cosine x, which would be sine x, and the derivative of the bottom would be 1 plus 2x. And so let's plug in 0 again. When we plug in 0 here, we get 0. And when we plug in 0 down here, we get 1. So that's not our indeterminate form, so we can go ahead and find the limit at this point. So it's 0 over 1, which is 0. So we need to stop. We got an indeterminate form of 0 over 1, and we need to stop. We don't continue to differentiate. If we do, bad things happen. So I just want to point that out. If we try to take the derivative again, we get cosine of x over 2. And then when we put in 0, we get a half. We get the wrong answer. So we definitely need to stop whenever we get that, whenever we get a determinant form. If we lose that 0 over 0 or infinity over infinity, we stop. We can evaluate anything at that point. Okay, so let's try this one. As we plug in infinity, we get infinity over infinity. So we can't factor this, so we need to use L'Hopital's. So the derivative of the top is 2x. The derivative of the bottom is e to the x. Okay, plug in infinity again, we still get infinity over infinity. So we're going to do L'Hopital's again. Derivative of the top is 2. The derivative of the bottom is e to the x. Okay, now when we plug in infinity, we get 2 over infinity, which is 0. So we stop differentiating, and we can get a value of 0. Looking at this is a really complicated one. But when we plug in 0, we get 0 on the top and 0 on the bottom. Okay, so we're going to apply L'Hopital's here. It's just a really complicated derivative. So the derivative of this is 1/2 1 plus x to the minus half. And the derivative of this is 0. And the derivative of this is minus a half. So that's the top. And the derivative of this is 2x. That's the bottom. So there's the derivative. Now when we plug in 0, we still get 0 over 0. So we have another L'Hopital's to do. So we take the derivative, bring down the power, we get minus a quarter 1 plus x to the minus 3/2. This is 0. This is 2. The derivative of this is 2. So we end up with this. Now when we plug in 0, we get minus 1/4 times 1 over 2. So that's no longer needing L'Hopital's. So minus 1/4 over 2, that means minus 1/4 times a half, which is minus 1/8. So the limit of that is minus 1/8. Okay, so we can also evaluate things that don't appear to be ratios. So for instance, and don't worry about all of these except for this one. These are all the indeterminate forms, but these are all BC applications. These aren't AB. But this one is this one disguised, right? I can divide by infinity, or I could multiply by 1 over infinity, which is 0. So this is a fraction in disguise, okay? So this is a fraction in disguise, because as we approach infinity, it's infinity times 0. Sine of 0 is 0. So we're going to rewrite it as a fraction. We're just going to take this and stick it in the denominator and call it its reciprocal. Now we're going to go ahead and differentiate this, because now we have 0 over 0. So the derivative of sine of 1 over x, we need a chain rule here, okay, is cosine of 1 over x times the derivative of 1 over x, which is minus 1 over x squared. And then the bottom here, notice it's the same pattern. The derivative of this, because this is x to the minus 1, the derivative of this is minus 1 x to the minus 2, or minus 1 over x squared. So the derivative is this. And don't worry about this comment here. I'll tie this in just a minute. But notice we have some things that cancel here. So really we're evaluating the limit as x approaches infinity of cosine of 1 over x. So we can put infinity in here and evaluate this. 1 over infinity is 0. That's one of our special fractions. So what's the cosine of 0? Cosine of 0 is 1. So we know that this limit is 1. Let's talk about horizontal asymptote questions. Here's a horizontal asymptote question. What are all the horizontal asymptotes of this graph? So that means take this function and take the limit as we approach infinity and negative infinity. We have to take the derivative of this. We're going to do a little reminding of what that derivative is. Think e to the x for starters. Okay, so to find the asymptotes, we have to do two limits here for horizontal asymptotes. We got to approach infinity from negative infinity and positive infinity. So let's do negative infinity first. Putting in negative infinity here gets us indeterminate forms. It gets us 0 over 0. And then here's the plus infinity expression. So we can see that this is, oh, my mistake. As we put in infinity here, this ends up being, we can just plug it in. We don't even need L'Hopital's, because 2 to the negative infinity is 0, right? It's 1 over 2 to the infinity, or 1 over infinity. And this is also 0, so that limit is 5 over 1. I forgot that we don't even need L'Hopital's here. Now let's approach a positive infinity. Okay, this is the problem here. So when we put positive infinity here, then we have infinity over infinity. So this is the one we have to do L'Hopital's on. So this one was just a straight plug and chug. So we're going to have to differentiate this. So if you remember, when we differentiate e to the x, we get e to the x. We really get e to the x natural log of e, which is 1. So that helps us with a different base. This base is 2. So 2 to the x, the derivative is 2 to the x natural log 2. And then this derivative is minus 2 to the x natural log 2. So looking at this, we've got a lot that cancels out. The natural logs cancel out, and 2 to the x over 2 to the x cancel out. So this ends up being 1 over negative 1. And so it's no longer indeterminate. We can stop using L'Hopital's. And so this limit is negative 1. So we have two asymptotes here, an asymptote at 5 and an asymptote at negative 1, which means the answer here is E. So at this point, L'Hopital's makes limits easier. That's plain and simple. If we have those indeterminate forms, we can just easily differentiate the top and the bottom, and keep doing that until we lose that indeterminate form, that 0 over 0 or infinity over infinity. So a couple of things before you jump into the web assignment. One, if you want to buy a prep book and do some prepping outside of class, the McGraw-Hill book, 5 Steps to a 5, I think it's called, is a great book. They also have an app. If you go to the App Store, search for AP Exam Prep, look for McGraw 5 app. The app is free, and I think they give you a fair amount of practice for free on the app. If I recall, it's something like 50 questions a chapter or something. So you without even purchasing it, you get a fair amount of review. So it's a good app to have just to do some extra review problems. I highly recommend it. And yeah, if we look at this here, when you download the 5 Steps to a 5, you actually get an option to download all of their a spattering of all of their books. So if you've got other AP courses too, you can download all of these. So that's kind of nice. Okay, so there's only one assignment for this unit, and it's the 8.1 limits and continuity. There's no proficiency quiz. So this one assignment is going to prepare you for that Blackboard test at the end of the week. Remember, again, that's all multiple choice questions. It's 30 of them in an hour, so it's that 2-minute pace. It's no calculator, because it's the no calculator pace, and that will be taken and scored on Blackboard at the end of the week.